Thank you, Flavia. Thank you very much. Okay, so I would like to tell you about a tool that we built that allows us to manage HPCC and AWS from the command line, because we find that to be much more useful. So before we start, I want to know if you can fill out this quick poll. So how do you run your HPCC environment? So you have a couple of choices for this, and so I'd just like you to go ahead and tell us how we do that. And we'll talk about this at the end of the presentation. So first of all, I'm not going to spend a lot of time explaining this, but the cloud is a really great place to run a lot of codes. There's a lot of really good reasons to do that. I mean, it's often cost effective, especially if you're just renting the cluster. So if you just need a cluster to do a quick job, it's much better to rent the cloud. Just like it's better to rent a tool from Home Depot before you don't need it. You don't need your aerator every day of the week. You just need it every day of the year. You just need it that once a year. So that's another good thing. Also, you can do it on demand. Not only can you do it, you can do elastically. So if your load grows you can grow your cluster in demand to solve the load. And often it's easier to come up with operational expenses than capital expenses. So for all kinds of reasons, people like to run in the cloud. And we wanted to be able to run in the cloud. And so what we were doing was doing a lot of testing in the cloud. And so what we found was that we had to we would create a cluster, and then we would run our tests on it. We would destroy the cluster. We'd create a different kind of cluster, different size, different configurations, and we'd run the test. And we were finding ourselves spending a lot of time in these really boring, really dull and tedious tasks of creating the cluster, because AWS is really well designed, and it works quite well. What it has is the standard way to do it is a GUI or a wizard, where you go through several steps to set up a node. So this is an example of the wizard, the GUI that you do for setting up nodes. The first step is you have to choose a machine image, which is the virtual machine is going to be overlaid with. It's going to contain the operating system and all the support programs that you get. So you need to select that. Then you need to select your type of machine, and there's a whole bunch of configurations for that. Then after you do that, you need to select some more details on this instance, and then you need to define the VPC, or you need to add storage in this case. Then you need to add security groups, and then you can launch it. And what you've done is, and there's actually I've hidden a lot of steps. There's a whole bunch of, each one of these different panels has a lot of choices on it. So there's a lot more steps in this, and all I've done is created one node. And as you know, HPCC is a cluster, so there's a lot more steps involved in this. So what I want to talk about is how we went ahead and simplified this for us, so that we could make it more of a command line interface. So first of all, there's a whole bunch of infrastructure on AWS that we wanted to deploy, wanted to enable to be able to use. So we had, obviously, the virtual machines are one of the key parts of it, and these are become the nodes in an HPCC cluster. We group those things into an auto scaling group, which I'll say a little bit more about later. And then we have to create a virtual private cloud, just because that's the best practices way to build a cluster in. Well, there's plus advantages, but that's best practices way to build a cluster in AWS. And we created security groups because we needed to authorize the different nodes to access the resources we have. And of course, you want to install your own platform. You want to install AWS platform. Maybe you have third-party solutions you want to also put on that same node, and maybe some other bundles that you have to put on nodes. So you have to be able to configure a lot of stuff. So we wanted to be able to figure out a way to do all this in a straightforward way, and that's how we did it. So one of the goals that we had in this was to make everything command line driven. We really like, the GUI and the wizard are great when you first learn a task, but once you've done it a while, you want to short circuit it, and a command line interface is the best way to do. We want to be able to have all kinds of flexibility within AWS and be able to manage AWS well, and also to do some HPCC systems commands on the to manage the cluster. We wanted to be able to save and restore the data, and we also didn't want to implement anything that already existed. We were quite comfortable using ECL to launch work units and using DFU plus to load things onto the cluster. And so we're going to go ahead and just not reinvent that wheel. We're going to go ahead and use that. And then AWS also has a similar set of command line tools that allow you to access their resources. But what we found ourselves doing was building scripts that, in order to launch these different clusters. So we built the script, and then we'd modify the script, and then we tried to parameterize these scripts, and it just became, it wasn't convenient. It was too onerous to do that. So we decided that it was a command line tool made a lot of sense for what we were doing. And so we went ahead and implemented this command line tool. And what we think is that while our needs weren't unique, they're certainly not common. Most people who use HPCC have a job they want to get done. They will have an answer they want to see. What we were doing mostly was trying to figure out if our optimizations were actually making an improvement. We wanted to know if they were, so we'd create a cluster of a size, check it, and then we run a program on it, turn it down, tear it down and run another cluster. So we were probably, like I said, not unique in our thing, but we're not common. But we think that the situation we're talking about is quite common, in that many people operate in a periodic workload environment where you execute for a while, get a job done. Let's say you have to produce a report for your sales manager every morning at 8 o'clock. Well, it probably doesn't take you 24 hours to run the report. So you fire up a cluster, you run your report for a couple of hours, and then you tear it down, and then you do that again, a few hours, soon enough to get it ready for 8 o'clock in the morning once the data gets there. So if you think about periodic workloads, and you assume that there's a lot of that's a common use case, then we break this tool down. We have the execute, and in between these execute phases are the idle phases. Now, we want to do all kinds of optimizations on that, but I'm not going to talk about how you optimize the execute phase. That's different. That's picking the proper number of nodes. That's picking the number of, the instances, the EC2 instances you want to use in each one of these nodes. So there's a lot of ways to do that, and that's pretty standard stuff. And while HaaS allows you to do that, it doesn't do anything special. You pick the number of nodes, and then it either makes it fast enough or doesn't. But what we do want to do for HaaS, we want to be able to make it easy to start. We want to look at the cost of starting before you execute and then termination. And so there's a couple other phases we want to think about, and that's the restore, which is what you have to do to get the data onto the cluster before you start the cluster, and then there's a save phase when to take it off. And between the execution, there's some cost that you want to contain when you're not doing anything, because you have persistent data that you want to hang on to between these executions. How much does that cost you? So we looked into all those. So looking at that, we now say first of all, I think this model applies to everybody's workload. I guess there's a few workloads where you start them up and you run them and never stop them, but I don't know even if that's the case, because you sometimes have to do maintenance. And so you'd have to, shut the cluster down and then restart it. So, I think it's fair enough to say that this is a common occurrence. So that's our argument that why this is a valuable tool. So one of the big things to consider is the cost of storage, and so that's the biggest place where we can actually make a difference in HaaS. It's how do we manage storage. Again, as I said, the execute phase really depends on how much you want to pay to get it done. You can get a big node and a lot of nodes and make the execution phase shorter, or you can not make it not shorter. And those are really independent. We didn't really have much. There's not really much to do for that. That's already available for you to make those choices. But we do think that we want to consider what's the way to store your data. So you have two uses of the data. You have the data when you're online executing and when you're offline. And so there's three general classes of storage that make sense in this environment. And one of them is elastic block storage, which is basically a disk. You just add a disk to the virtual machine. A virtual machine comes with some instance store, but it's a very small amount of instance store. It's enough to run your operating system and maybe hold temp space, but it's not enough to hold any application data. So you have to add, if you want to run your application, if you want to run an HPCC cluster, you have to add storage. And so one of the ways to do that is elastic block storage, which just basically sticks a disk on your drive. It's like plugging in, like adding a new disk to your laptop. And so you can store that there. That's a fairly cheap solution. There's a lot of different choices you can have. One of the general purpose solutions is 10 cents a gigabyte a month, per gigabyte per month. And that's a good solution. There's another solution that you can have, which is EFS, which is basically Amazon's NFS server. You launch an NFS or a SIPS server using Amazon resources. That costs 30 cents a gigabyte per month, and the reason it costs more is because it is more. It's an NSF web server, so it not only has the storage, it also has the server component. So it has some EC2, some instance, EC2 instance running on the front end of that. And unfortunately, I can't compare this, or I'm not able. It's too complicated to really compare the trade-offs between a remote file system and local storage. I mean, there's some huge advantages to remote file system. For example, it always exists, and it exists regardless of whether your cluster's there or whether you have multiple clusters there. So you could have, if you wanted to run 4 clusters, you could service them all from your remote file system. And so that there's more trade-offs here than I can actually illustrate. But I wanted to show the simple case where I'm running one cluster off of one set of data and at least evaluate that system. But EFS is a very good solution, but I don't think it's the solution that many people will choose because it's pretty expensive. So now the other solution that we're all advocating is to use S3. Now S3 is a great solution for offline because S3 is an object store. So it's not something that HPCC systems can use natively. HPCC systems really wants to see this as a block device. They really want to read that, and not an object-oriented device. So it doesn't make, so it's really only an offline solution, but it's a very good offline solution because it only costs you about 2 cents a gigabyte per minute. So if you're not online, it's better to store it in S3 than it is to store it in either of the other options. The problem, of course, is that if you store it offline, you have to use something different online. And so now what we look at is we now have different values for online and offline storage. We also have in this last one we introduced the two new stages. We make the save and restores much bigger. It's much more, the save and restores are fairly cheap for elastic block storage. You just have to mount the drive, and same thing with NFS. You just have to mount the remote file system. But for elastic storage, you have to copy the data, and you have to, either on a save or on a restore. So it does change the equation a little bit, but it is a huge savings. And so if you look at if you look at those numbers as a graph by utilization, if you look at the utilization, you can see that the knee in the curve for S3 is versus the elastic block storage is at 77%. So if you're working around 19 hours a day or 23 days a month, then you don't need to use S3. But if you're somewhere short of 19 hours a day or 23 days a month, I think which is a lot of applications, then the S3 is a good choice for you. And so that's the solution we provided, and that's the way that we use this. So now getting to the basic architecture that we built, and so there's a lot of best practices that go into what we've designed here, and I don't have time to go into all the details, but we used a lot of the techniques and tools that S3 allows you to a lot of the tools that S3 has, that AWS has, in order to support this cluster and build a really good cluster. So one of the things we use is something called a CloudFormation template, which is a really nice way of creating your architectural design, and it's a parameterizable template. So it's the template is JSON, and you can put parameters in there like number of nodes that you want in that. And then you can just say, to AWS, execute this template, and then it will create your cluster. So that's the way that we were able to deploy the AWS cluster. But we did design the cluster itself. And so what we built was we decided we were going to do an N+1 cluster, so N slaves plus 1 master. And we put we put the master in an auto-scaling group and the slave in another auto-scaling group. And now this is a sort of a misnomer because we don't really use the auto-scaling part because HPCC systems is not quite ready to be elastic. It needs a little bit more features a little more capability to be truly elastic. But the group gives us a lot of convenience. For example, we can launch all the nodes in the slave system with one command in that group, and it creates all of them, and it creates all the slaves in that node, and they all can talk to each other, and they know about each other, and they have the same resource utilization, the same roles and stuff like that. And so it's really important to use the group. So the auto scaling is just the name of it, is just a feature we don't use. We set the minimum and maximum allowable number of nodes to the same value, so it won't scale. But the reason we have two auto-scaling groups is because we wanted to be able to deploy a master node that has a different configuration than a slave node. For example, we found that the master, it might make sense to have the master have a little bit more capability or a little less or a little less capability in certain features. So we could configure the different. We could use a different EC2 instance for the slave as for the masters. And then the last thing, and then this is all inside of virtual private cloud, and there's a whole bunch of other things that go around this CloudFormation template, which I won't talk about. But that is how we deploy a cluster. But we can parameterize this. We can say the type of instance we want. We can take the number of Thor nodes, the number of Roxy nodes. We can decide the number of disks and the size of the disk that each one of these nodes has. And so that's pretty convenient. We can do that all at the command line. So the CloudFormation template is a command line argument to HaaS, and all these other things are also command line arguments to HaaS. So HaaS is a purely general tool in that respect. The last thing I want to talk about is the custom AMI. So an AMI is an Amazon machine image. And what that is that's what, when you boot the node, that's what gets loaded into the system, and it contains the operating system and all the programs that you want. So you have to have, in order to use the way we did it was we started with a bare bones Ubuntu implementation, and then we installed HPCC systems, and then we installed a couple of the bundles, and then we would install some software from HaaS itself to run on the individual nodes, and then we saved it and saved that as an AMI, and so then we had to specify that AMI in our arguments to pick that one to run it. So this is basically how you create a cluster, and you create the instance inside AWS, and so AWS calls it a stack. So we call this the stack. So HaaS has is a command line argument. So the command is HaaS, and then you have a major command, in this case stack, which is to implement to create the instance, the cluster, and then we have several commands that you can do off of that. And what you provide to that is you provide a CloudFormation template and a whole bunch of parameters. The AMI, the number of Roxy nodes, the number of Thor nodes, all those different configuration parameters you want to configure. And then you say create, and it will create all these resources in AWS. And after a period of amount of time, several minutes, it'll come back and say everything's been done. And you can also do a couple of other things. You can delete it. You can look at the resources that you have, and you can monitor some events. Because if AWS has a failure or something can go wrong, you might want to be able to see what's going on, and you can see the events directly from the command line. The next major command that we have is the cluster command, and we use cluster for HPCC systems cluster, and we use stack for the resources that AWS provides. And cluster, primarily, we do start and stop. And there's a few things you can do. Status, which just makes a call into the HPCC systems and gets back the status that you get from HPCC systems. The third command that we have, major command that we have is data. And so the idea here was that, remember, we wanted to save and restore. Well, that's a command that we, as HaaS, did. That's one that we have to manage. Oh, I meant to say on the last slide that while we're doing that, while we're doing the cluster, primarily while the cluster's running, we're using ECL and DFU plus. And so that's how we manipulate the cluster. And we didn't reinvent that. We were very comfortable with ECL. It's a great command, and it does everything you want to do on the cluster. So that's how we run the cluster. But how we provision the cluster is through HaaS. Okay, so now one of the things that that wasn't easy to do with DFU plus, because it ran on our laptops, was the save and the restore. So we added some data sources that did this command, this set of data commands that allows us to save and restore resources. So what you would do is on the save, what you do is we bundle up the resources on the slave nodes and possibly the master, and we write those out to an S3 object. So the way that we chose to do that was we have scripts on all of in the AWS instances, and so this command invokes a script on that. So if it's a save, we tell it to save the resources and write to an S3 object. And that way the resources don't go to your laptop. They just go from EC2 right into S3, and they stay on AWS, which makes a lot of sense. And we do the same thing with restore. The way that we do this is, so we allow the data to save any logical file in your distributed file system, or we also save work units because we sometimes want to restore those work units, and we also save any files that you may have uploaded into your drop zone. And so so what you do is you pick the resource that you want to use. So you say HaaS data save, and then you give it a resource name, a name of an S3 object that you're gonna save it to or restore it from, and then you decide whether you're going to what resource you want to use. And so we allow you to do a regular expression, so you don't have to save every file that you have in your DFU. And the other thing that we've done is that we understand a little bit about AWS, so we're able to leverage AWS. And in particular, what we do here is in this case, if you save 10 nodes, this shows the first three objects that we create. So we're going to create, the base name is 10 nodes. We've saved the files in the distributed file system, and so we saved it for the first node. We saved it in -1, then in -2, and then -3, and it goes on. And so what we've done is the save command is invoked on all the slaves. We do a tar g and gzip that, and then we copy that from the S3 slave node directly into an AWS object. And we take the base 10 nodes and append the proper suffixes on that, so that we can identify it as a DFU object. The other thing we've done, though, is we prepend some arbitrary strings on top of that, on the front of that. And so this arbitrary string isn't that arbitrary. It says HPCC is awesome. And I guess we didn't think it was completely awesome because we didn't spell awesome correctly. But we use a random sequence of bytes in front of there because we want to exploit the locality that's in S3, or actually we want to exploit this locality. So S3 puts objects on their different resources based on the first few letters of the name. So if we began all of these S3 objects with 10 nodes, then when we loaded to, say, 10 nodes, or even to 100 nodes, all of the slave instances would be asking the same S3 resource for the objects, and we wouldn't get as much parallelism. But if you randomize the first few characters, then you're highly likely to get 100 different S3 resources replying to those 100 different requests. All right, so the other thing that we in addition wanted to be able to have some flexibility here, because like I said, one of our goals was to create different size objects, was to test this on different size clusters. So we also created a data resize operation, and suppose we create a 4-node instance, and then we restore a 2-node instance onto that 4-node instance. So it's going to, by default, HPCC is going to just load that onto the first 2 nodes. And then so we wanted to be able to resize that onto that 4-node instance. And so what we do is we take those 2 parts, so the DFU, let's say it's a DFU file, it's going to have 2 parts. That logical file is going to have a part for the first node and the second node because it was stored from 2 nodes. But we want to create 4 logical parts. Well, what we did was we just run the distribute command on HPCC, and we were able to distribute it to 4 nodes. You can also do it from 4 nodes down to 2 nodes, but it's a little more complicated. So I'm not just going to show that example. Just to give you some flavor for what this takes, the save and restore are expensive operations, and so it takes many seconds to do this. But it's roughly linear as the size grows. And the other thing to see is that the restore is significantly faster than the save, and that's because you don't have to create the S3 object when you restore. You're just reading from it, and so it just ends up going a lot faster. Here's a sort of a flow chart just to give you an idea how long it takes to boot up one of these clusters. So this is a 4-node cluster, and what we've done is we've compressed the log that we get back from AWS, and we've shown it a little more visually. So we're creating a single AWS stack with the CloudFormation, and everything that's in that, all these resources belong to that stack. And you can see that it creates a couple of things, a couple of EC2 instances, including a virtual private cloud. Then it creates IAM, which stands for Identity and Authentication Manager. So that's a role, and then you get an instance of that role, which allows you then access to those resources. Creates those things, and you can see when they start and stop on this timeline. It takes about 5 minutes to create this entire cluster. And at the end, you see we create, the last 2 things we created are the auto-scaling group. So we created 2 auto-scaling groups. One is for the master, and one is for the 4 slave nodes. And it takes a little bit longer to install 4 slave nodes than it does to do one master node. And then just to summarize the command set that we have for HaaS is there's 3 major commands. There's stack, which is to provision the AWS instances, the resources on AWS. Cluster is just to manage the HPCC cluster system. To run the cluster, use ECL. And then the data is to be able to do save and restore. And then Resize was very useful. We found very useful as well. So if you find this interesting, there's the GitHub repository. It has gotten kind of a little bit inactive because my graduate student has graduated. He's no longer a graduate student, and he's not working in AWS. He unfortunately didn't get a job in HPCC systems, but he's happy with his jobs and he's making money, so we can't complain. But if you'd like to help, that would be great. And so now that I'm about done, but I'd like you to take this poll, which is, do you think or would you have a need to use HaaS? And so please answer that question. And I think that I get to turn it over to Bob at this time.
All right, Vince, thank you so much. That was a wonderful presentation. We're going to first of all take a look at your first poll question, and meanwhile, go ahead and take a look at some of the questions that came in, and you might want to prioritize the ones you want to answer first and second and so on. Meanwhile, let's take a look at the very first question in our poll, which was, how do you run your HPCC systems environment? And we had 25% that said they're in the cloud, 18% that are using it as a single node on a VM, and we had a good 43%, almost half the people out there in the Tech Talk use the internal data center, their own internal data center. Only 6% externally hosted and 6% not currently running HPCC systems. So that is the first poll question. And I'll tell you what, let's go ahead and take some questions from the audience, and then we'll go through the second poll question. Before Vince, I turn you loose on that, there was one question that came into both myself and Flavio regarding if we have any TED Talks conferences with HPCC. And, well, the answer to that is not presently. We don't have any TED Talks planned, but we do have many other events where we're always speaking at trade shows and universities and such. So the best answer to that is to check our HPCC Systems website and click on the events link to get to the appropriate talk in your area. So let me just mark that as answered. Also, thank you from the Princess Leia Lucas Foundations. We really appreciate your thank you. That was wonderful. And thanks for being here at the Tech Talk. So, all right, Vince, I'm going to give the floor back to you to answer a couple of these questions. Question number one, what other research are you doing at NC State that leverages HPCC systems?
So thanks, Bob. That's a good question. So right now, my previous work has been a lot in the systems and making in finding ways to make HPCC run more efficiently. What I'm doing now, though, is actually using HPCC, and so it's kind of fun to be a user rather than just playing with HPCC. And so the current work we're using is we call Athlete 360, which is 360-degree view of an athlete. So I'm working with the strength and performance coaches here at NC State who manage athletes over 21 different sports, and they have found there's a disruptive disruptive technologies in sports now, which allow us to monitor athletes in very creative ways. We have GPS units that tell you everywhere they are during practice or on a game, and we also have heart rate monitors. But we also have we're monitoring gym equipment, so we can see we can see velocities and accelerations on their movements, and they can take all this data, and it can be a large amount of data, and they want to do some predictive analysis on it. For example, to say maybe onset of injuries, to say, oh, you're getting we want to, you need to be careful because you're ripe for a hamstring injury, which a lot of our soccer players get, and it takes them out of action for a while, and it's hard to recover from that. So there's a lot of different predictive analysis that we'd like to do to improve athlete performance, both their readiness and also their recovery from injury.
Okay, fantastic. Another question, who could most benefit from using HaaS, HPCC as a service? Could other universities take advantage of this?
Well, yes, so certainly anybody can take advantage of this, just download it from the GitHub website. I think anybody can use this. I mean, whoever would prefer to use a command line, which once you've gone through the screens, 15, 20 times, you would rather use command line. And there are command line tools. There's AWS command line tools, and there's there's ECL and DFU Plus, stuff like that. And if you've ever used those, you understand that these are much better for an expert user. But the problem is that AWS, you still have to script it to deploy an HPCC stack, a stack for an HPCC system. So it's just kind of nice to have this wrapper in there. Plus, you get the programs that run on the slave nodes itself.
All right, great. And the last question, I think I might even be able to answer this after listening to your presentation. It says, do you need an AWS account to use HaaS? And I say that's yes, right, Vince?
Absolutely. The answer is yes, you do. One of the things that's nice, though, is you can AWS. It's kind of like a drug, and they just want to get you hooked on it. And so what they'll do is they'll give you a free year. You can operate for a year on the free tier, and you can't do a lot. You're not going to be able to mine bitcoins very well with that, but you can within that free tier you can create some small HPCC clusters, and you can experiment with it, and so you can do it for no cost.
Oh, fantastic! All right, so Vince, I think let me just go ahead and review our last poll question. We got some really great news about this one. The last question, would you have a need to use HaaS? And yeah, over half of the people at the Tech Talk said yes, 54%. So that's wonderful. And, I just want to thank you for a wonderful presentation, taking time out of your day to review and present this technology to us. And hey, I'm looking forward to seeing you again at All Things Open maybe this fall. What sounds like a plan, right?
Yeah, yes, it does. And maybe I'll see you in the community day too. So.
Sounds great. Looking forward to it. All right.
Thanks, Bob.
So, yeah, thanks, Vince. Thank you. And